Okay. Sorry, Stefano, you should put it in. Okay, yeah, good. So good afternoon, good evening, everybody. So we are fortunate today to have the head of the upload team with us. So he's the director of the Center for Autonomous Materials Design, Material Science in Duke University in the US. And he heads, it's his team that is producing all the data that we are using on upload. Okay, so between October 2021 and now, his team has helped with some training of all of us, training us how to use upload. So there was Mark Westers and there's Cormac who worked with us to do the training. So he's the boss of all of them. Okay? So we are fortunate to have him here to give this talk. Okay. Yeah. So over to you, Stefano.
Thank you. Thank you very much for the nice introduction, and I hope you hear me well. I put the headphones. If you have any questions, just raise the hand or just interrupt me. No problems. We are here to learn. Okay. So can you see the mouse?
No, we can't see the mouse.
So Stefano, you don't mind if we eat bananas while you're speaking, huh?
Say again?
You mind if we eat bananas while you're speaking?
No, you can do whatever you want.
Thank you. You don't see the mouse. Is it red?
1 second. Okay, can you see the?
Yeah.
Okay, perfect. Okay, thank you very much. Thank you for the invitation. Thank you for the presentations. So today I'm going to talk about what we are doing with the data and how we are studying. We're using it to study disorder and how to study new materials that in this case are high entropy ceramics. And we have some work that I want to share with you. I want to thank my collaborator, Cormac Toher, now is professor at UT Dallas. Corey Ozis is a current postdoc of mine, but soon is going to become an assistant professor at Johns Hopkins. Marco Esters is a current postdoc of mine, and he will look for he will live in the fall for a corporation job. Okay, so the sponsors of this research is Office of Naval Research and National Science Foundation and the Army, which is giving us a lot of computer time. Okay, so why we are looking into disorder? Well, actually, it's kind of obvious why we are looking into disorder, because we want more functionalities. We are never happy of the materials that we have. And therefore, when we add more functionalities, we want to add more species. And what happens as an outcome of adding more species to the mix is that you have order-disorder transitions. This is an example. This is a material science 101. For instance, if you have a copper-nickel alloys, right? So this is a pure FCC in copper rich and pure FCC nickel rich. If you keep adding species and if you are near the center of the phase diagrams, you see that you have this line, which is called miscibility lines, which separates the region of mostly order with region of mostly disorder, right? This is really a schematics. Note that when, as a physicist, we discuss order, disorder, we really believe that the order is really, really order and disorder is really disorder. In reality, there are a lot of things in between. You can have, for instance, in disorder, you can have high macroscopic entropy, meaning that or if you mix the red atoms with the blue atoms, you have some color in between and no microstructures. And when you have order, you might have a ordered set of microstructures, but inside you might have a disorder population. So the way to have order disorder is not really like what we do with the ISIN model, where you go completely order to complete disorder. And therefore, it's much more complicated and we need to address it. Why? Because this changes dramatically mechanical properties, okay? If you want to know about how people deal with these things, you can, Cormac and myself, we wrote a review here at Entropy Ceramics, and you can see on the bottom right the DOI and the references, okay? All right. Okay. So why we believe that disorder is unavoidable? This is actually work that was made by Cormac and myself and David and Corey, and actually is using our machinery to get automatic convex salts. Right. It's part of the EAIFR consortium. Anyway, so why disorder is unavoidable? Because if you mix, let's start with two species. It's very simple. You take A, you take B, right? You mix them, and then you calculate with a VASP or quantum express. So you calculate a bunch of formation enthalpies of various configurations. Some will be positive, so no mixing. Some will be negative, so mixing. And then you construct this blue line or this black line, depending, if you want the max or you want. Okay, so let's not go into details. Anyway, you calculate this. What is called this convex sol, okay, which is pretty much the envelope of all the possible combination of these dots, right? You can use machine learning, cluster expansion. So with a bunch of these red calculated ab initio calculated structures, you can get all the infinite one that you want. Okay, this is all. It's very tedious in 2-dimension, but you can do it by hand. But if you want to go in more than 2-dimension or 3-dimension, you need to use this kind of tools like what Corey has generated. You can get this online. Okay, so once you have all the possible A and all the possible B's, right, you make an average of this. Okay, so you get like 100A, 99B, so pretty much 5,000 of them binaries. So it's going to take years for you to calculate, but you can do this average, and you can calculate what is the expectation of formation enthalpy for a two-species systems, right? So it's pretty much you take the bottom, then the bottom, then the bottom, and you average them with this average, right, with the brackets, and you get this H2. So H2 means that if you take whichever A and whichever B and you put it together, then you have an expected amount of H2. Okay. So now, what about if you do with 3-dimension? Well, 3-dimension becomes more complicated because remember, thermodynamics is a survival of the fittest or survival of alliance between the fittest. What does it mean? It means that if I have a ternary phase diagrams, you have A, B, C, right? The A, B is going to be ruled by what we did before. BC is the same, AC is the same, but in between, okay, you might have an alliance between the other dots, okay, which are in the minimum of this multidimensional convex sol, in which they ally together, so they lower the total Gibbs free energy. Okay, so pretty much you need to calculate the total convex sol, all right, and see how these things interplay with each other to find the proper decompositions. Okay, so if you have 100A, 99B, and 98C, and you just do this 100 times 98 times 90, well, 99 times 98 divided by 3 factorial, you get pretty much 30,000. We did them all. This is an example, right? So you get all these pictures, and then you make an average, and you get a number. Okay. Of course, since you add species, there is an expectations to go deeper in this convex sol, right? In fact, there is, because this thing is kind of looks like a sink, and then more species you get, the more deeper you get. But the rate at which you get deeper, which is this gain 2 to 3, and now we can do n to n plus 1, actually decreases, and that's the trick. Okay, so what happens? So to calculate these things, actually look at here again, from going to 2 to 3, from n to n plus 1. So Cormac and I, when we wrote this very short paper, this is like 1-page paper you can read in 10 minutes. Okay, defined this gain as you take the convex sol that you can generate with n system based on n minus 1 subcomponents. Okay, so you have n minus 1 subcomponents. Okay, so you're going to have an hyperplane, and then you have this gain, which is this amount here, that is the real n gain with respect to the n minus 1 subcomponents. Okay, so this is could define as the delta convex sol, which is very simple, and is pretty much a recursive expansion of the usual convex sol, right? So if you do sum all this delta, you're going to get the real convex sol, which means the real Gibbs free energy. But this is very useful because it's this arrow which is actually fight for against the disorder, right? It's not the total enthalpy, because you might have a sublattice order, but it's really this object one. Okay, so you need to compare these objects, which can be calculated with Corey-Aflow-Hall, right? And then compare this with the disorder promotion that comes from excuse me, from entropy, vibrations and temperature, etc., etc. Okay, so this is actually what happens, right? So we plotted the red arrow, right, with respect to the number of species. This is a cartoon. In a couple of minutes, I give you the real numbers. Okay, and we see that actually this the promotion, right? So how deep the convex hull grows with respect to the increase in number of species, actually decrease with the number of species. All right. So look at here. If you add disorder, which means that you add x log x, like random, complete random solutions, or you think that here there is one sublattice that is order, or two sublattices disorder, or three sublattices disorder, etc., etc. Okay. Then you see that there are three regions of the space with respect to the number of species. There is a region of low entropy where everything is dictated by enthalpy. Okay, so here this is where you would, let's say from 2 to 4 species. This is where you would to find the most stable configuration. You would really have to minimize the enthalpy. This is what we have been doing for 30 years. Then we have on the other side, you have when you increase the number of species, you have a region which is entropy stabilized, where you have as much entropy as possible, and you see that entropy really rules, no matter if some of these sublattice are ordered, right? So pretty much here you don't care anymore about enthalpy, and everything you need to care is about entropy. Okay, and then there is another region in between where there is a little bit of entropy, a little bit of enthalpy. So you need to pretty much balance them together and see who wins. All right. So the entropy stabilized region is where entropy stabilized oxides do exist. This is what we discovered in 2015. And then high entropy systems are like high entropy carbides, high entropy borides, etc., etc. And objects that were discovered for carbides by us in 2018, and for borides by Luo and Vecchio in UCSD in 1 year before. Okay, so pretty much depending on what you are looking for, you need to consider which balance is going to win. And now about the numbers. Those are the numbers that we were able to extract by Cormac, Corey, David, and myself. These are real numbers coming from our database. So if you add two compounds, meaning that if you mix A and B, you have an expectation of generating 185 milli-electron volt. Okay, all right. So this to 185 milli-electron volt, if you compare to room temperature entropy, which is roughly 25 milli-electron volt for two species systems, right? This, you see that this is much bigger. 185 is much bigger than 25, so you pretty much entropy does not play a role. But if you go on the ternaries, look at here, only 15% of the ternary compounds, okay, have a stable ternary configurations, all right, and are not split into sum of binaries, right? And the gain is only 7 milli-electron volts per atom, which if you compare to room temperature entropy, okay, x log x, is pretty much lower, right? And then if you look for quaternaries, look at here, you have a 1 milli-electron volt only push towards stabilization, which if you compare with the various entropy is pretty much negligible. So now you understand why quaternary compounds and pentanary compounds, if you go into the ICSD database, they're most, this is the case of metals, they're most likely disorder. So that's why there are no order phases reported for metals for 7, 8, 9, etc. species. Looking for them is really a waste of computer time, and it's waste of time, right? That's why both yes.
Yeah, but the DFT is not this accurate, no?
No, this is DFT data.
Yeah, but the accuracy of the DFT method.
No, because even if your DFT has errors within a 2-3 milli-electron volt, here you are talking about ideal entropy that are 30-40 milli-electron volt per atom. So you pretty much you are engulfed by entropy. This is really physical issue that you cannot avoid. If you are on ternaries, then you say, well, I have this Euler's. Is this stable or not stable? Well, let's use the better DFT. Maybe this can be questions. But for quaternaries and pentanaries, you have no hope.
Okay. Yeah. Thank you.
Yeah. Thank you. You're welcome. Okay. So here this histograms actually show how this phase diagrams, right? This convex hull gets squished, right? So this is the histogram of the number of alloys systems with respect to the enthalpy gain. You see that for binaries, it's very spread. You see that you have even 800 1 electron volt per atoms. But you see that once you get the ternaries, quaternaries, actually everything gets squished toward the zero. And despite the number of configuration increases. So this is number of configurations increases logarithmically, right? It's a log plot. So even if the number of configuration is exploding, right? Because it's just you have more configuration and this explode factorially, right? Then their value, their weight is rapidly going towards zero. So they will not play again, because at the end, when you have x log x that is the order of 25, 30 electron volt, you can have as many configurations as possible, but they will not simply appear. Okay. So this is another plot that shows how many of the 4-dimensional systems that we have scanned have a stable configuration. Only 50 over 100,000, right? So practically looking for, this is for metal, looking for many species order systems with DFT or experiments is really hopeless. Just simply do not form. Okay, so how do we model these things? People have been trying to model disorder for many years. Okay, so let's start from something simple, right? Okay, let's neglect high entropy stabilized oxide, because in this case it was all x log x, right? This beautiful work without any quantum calculations. So let's try to understand something in between high entropy carbides. Okay, so how do we calculate entropy? So, well, listen, entropy is actually a big beast, because entropy is even more difficult to calculate than enthalpy. Because as you remember, entropy is the generation of a state. So you need to get the states, see, and start shuffling around and see how many energies, how many states have energies between E and E plus delta E. Okay, and this is going to be the big omega. You make a log, and then Boltzmann tells you that this is entropy. So to get entropy, you really need to get a lot of states. And this is what we're going to do, because every state is a quantum calculations. So our assumption is actually the assumption of everybody, is that this order is pretty much a combination of order structures. So this is really what happens, because if you are making, think about it, that you are putting tiles on your garage, right? And every tile has a different decorations. Okay, if you are far, you don't see the decorations. You just see everything kind of mixed up colors, where some are blue, some are green, some are snakes, some are different cars, some are different kind of designs. But if you're far enough, you don't see that you have order systems. So as many of these tiles you need, actually that is the trick, because you need as many as possible, right? Because you want to scan as much disorder as possible, but at the same time, you want to have as large as possible, right? Because you want to have a disorder that has as much a longer range order as possible, long range disorder as possible. So when you do these expansions, right? So you have a choice. That's the key. You can choose to make a big order cells and few, because you don't have much computers, or you can choose to make many small order cells, but you have many. So we choose the second one because there is a fundamental difference between the two, and I will show you in a few slides. So when we generate many order structures, we take a conventional cells, right? Like for instance, zinc sulfur selenides right here, right? You just where you see that this is typical of a VASP input file, where you have an input file that has a partial occupation, and this defined in AFlow language is defined as a part car, and you can make from your in cars, you can make these part cars. You can go online and then generate all these configurations, and then there are translations for quantum espresso, for a binit, etc., etc. So you just can play on these things. So once you have your conventional cells, pretty much we create the super cells up to a certain volume, and the volume is given by this Hermite normal form super cells. So you enumerate them. There are not that many. Okay, given a volume, there are not that many, and then you scan them all around, and you remove the one that are symmetrically equivalent, the one that are equivalent by translations. Remember that there is not only the space group, there is the factor group, so it might have a translation of a that is inside degrees of freedom. Okay, so which is not in the lattice. So there is a lot of technicality, but everything is done by our AFlow sim code that has been made by David. So which calculates the unique ones, and then it gives the degeneration, this G. Okay, which is the cardinality of the factor group. Okay, so once you have these things, right? So look carefully. You calculate them all. You use C-HAL to calculate the ground states, right? You know, the minimum, and then you have the energy of all these things. So you have this activation energy. You see the distance from the convex hull. This is going to be the enthalpic cost, and then you're going to have the entropic gain that is going to come later. Okay, so since you have I, okay, so you have 8 of them, 100 of them, 1 million, as many as you want. This takes is going to be a Boltzmann vector, but sorry, Boltzmann coefficients. When you put the temperature, you're going to have a Boltzmann vector. Okay, so this is a big Boltzmann vectors. All right. Okay, forget about the technicality of the normalization. Okay, so just think about the numerator. Okay, so this is a normalized Boltzmann, hyper Boltzmann vector. Okay, so why we choose many with respect to large? Look at the competition. The competition SQS, right? The special quasi-random structures that were proposed by Zunger et al. And they're very good actually to understand completely miscible systems. Okay, so how the SQS are generated? There are very nice software like ATAT to generate them, and they're all over the place. Okay, so pretty much people decorate the crystal structures. Okay, right, the lattice. We work with Wyckoff positions, so we are more general, but that's not really big deal. Anyway, so they decorate the lattice. Okay, and then they calculate from this lattice, they calculate the clusters and the correlation between clusters, binaries, ternaries, quaternaries, etc., etc. So for an ideal, okay, so you can calculate these things. For an ideal disorder, okay, this cluster, sorry, these correlations are actually analytical. If you are a 50-50 compositions, and one position is black with 50% probability, and the other is white with 50% probability, then correlation is like 0.5 times 0.5 is like 0.25. For a ternary is one half cube. For a quaternary cluster is 1/2 at the power of 4. This is if you are 50-50. If you want to go in a different compositions, you can generate them all. But what is the message is that for the ideal disorder, the clusters can be, the correlation of the cluster can be calculated analytically. And you can look at the Zunger paper. Is I don't know, I don't remember if it's PRL or PRB. It's a 90 or 92. You can ask me and I send you the paper. And you see how they are generated. So of all the possible configurations with the right, with their own correlations, the one that most mimic, so the one that most resemble the ideal scenario are called special. So the special quasi-random structures are ordered structures that want to be disorder, ideal disorder systems. So, but think about where you have the ideal disorder. Ideal disorder exists only at infinite temperature. And infinite temperature, there is no phase transitions. There is no latent heat. It's like a gas. So SQS really, it's very good because it helps understanding a perfectly miscible system like copper gold, like silicon germanium, etc., where your species completely mix, and therefore you do not worry anymore about entropy. You do not worry anymore about phase transitions. But if you if you take the spectrum of these structures and you bring them at 0 temperature, you will never have any phase transition. Why? Because they all represent ideal disorder. So if you have a linear combination of ideal disorder, you get ideal disorder. There's nothing you can do. So the way that's why we stopped using SQS and we generated POC, which look at here, are small cells, but they are shuffled around. Yes, we suffer a little bit because we cannot really reproduce long range interactions, but they do reproduce latent heat and they allow us to give us phase transitions. That's the trick of our system. Okay, all right. Okay, well, there is also another advantage that is computational, which means money, because calculating many small things, it takes less electricity than calculating bigger cells, because the electricity goes like the cubic of with the time, which is the cube of the number of free electrons. But that's okay. Sorry. Anyway, so given a fixed amount of computers, if you want to get phase transition, you need to get our expansion, not SQS. So now that we have all our thermodynamic excited states, are all these red dots. Okay, so they are thermodynamic excited states, and these blue dots is given by the convex hull. Okay, so now we have now how do we define entropy? Well, technically, this is already entropy, but it is, but it is not. It is because it really, the generation of these things really indicates entropy, but it is not because we have only calculated a finite number. You should calculate infinite, but of course, we do not have infinite computers, so we cannot really do it. So we call this as entropic forming ability and not really entropy. So the entropy forming ability is really defined as, you see, as the thermodynamics density of states, similar to the electronic density of states. You have accumulation of these objects, you see, and if the peak is narrow, then you have a lot of entropy. If the peak is broad, then you have a very low entropy. All right. So for us, entropic forming ability, you get the spectrum of the excited states of the enthalpy at 0 temperature. Okay, and then you get the variance. It's very simple, right? So big variance, you're gonna have is gonna have low entropy. Small variance gonna have high entropy. So that's why you're gonna get -1 here. That's very simple, right? And it's normalized. Yes, there is no Boltzmann factor, etc., but it's extensive because the number of states increase extensively with the number of the size of unit cell, etc. So it has the capabilities of the entropy, but it is not an entropy because we do not have infinite red dots. Okay, so this is the definition if you want the sigma, but everything is done with this David paper, and then plus the Cormac one that to calculate these distances. Everything is kind of automatic. Okay, now let's use to study new materials, because at the end theory is as good as we find the new systems. So we're interested in metal carbides. Here you have a refractory metal metals, so you have 8 of them, plus you add some carbon, and then we say which are the 5 metal carbides that will form. We already knew from from oxides that the sweet spot was 5 metals. As I showed before from the unavoidable disorder. So we know that we need to have a 5 species shuffling. So we have for each one of these 5 combination of metals plus carbon. Okay, we calculate all this POC configuration, and then so there are like 100 of them, and then we calculate the entropy forming ability. We rank them from a big EFA to low EFA, and then we give them to the experimentalist without telling them which is which, so you don't bias them. Okay, so look, this is what we find. We find that the one with high entropy forming ability forms solid solution. Look at experiments here, and we see that the one with low forming ability, we have multiphase. All right, but look carefully. The top 2 systems, right? Okay, actually the second one, we start from the second one, right? Is this one. This one has hafnium, niobium, tantalum, titanium, zirconium, carbide, right? This was discovered by some our competitors, a couple of months before us. Here, these are the references, and you see it has a lot of entropy gain, okay, and very little enthalpy loss. Okay, this is kind of obvious. In fact, those are experimentalists, and the reason why they did this is kind of obvious because hafnium carbide is cubic, niobium carbide is cubic. all precursors are cubic, are already rock salt. So if you are mixing rock salt powder, what do you expect? I'm going to have a rock salt entropy stabilized system or high entropy system. That's exactly what they did, because the outcome is rock salt. So pretty much by understanding that the precursor were rock salt, an experimentalist can infer and can say, well, okay, this might be good test to the test systems, and it's going to show up. Effectively, it does show up. Very little loss in enthalpy. Okay. But the best one we have, which molybdenum, niobium, tantalum, vanadium, tungsten, carbide, actually is not a mix of rock salt, because molybdenum carbide and tungsten carbide, they are not rock salts. So now you're mixing three powders that are cubic with one powder that is rhombohedral, which means hexagonals. I mean, you can really make a nice tile in your garage if you have square tiles and the triangular tiles. You don't really cover everything. Plus a tetrahedral or octahedral one. I don't really remember. Anyway, so some of these things are not sorry, tetragonal, right? One is tetragonal, right? Some of the systems are not cubic, right? Okay, molybdenum and tungsten. So in fact, it was not predicted by experiments, and the only way to find was our systems. Look at here, the loss in enthalpy is very high, meaning that this is very high from the convex, the bottom of the convex hull, but it still has the highest possible entropy forming ability. Still, this material was found. So you see that nobody here would ever, in this, we are all computation here, nobody would ever even bother calculating an excited states with 156 milli-electron volt per atoms. The questions from our colleague before was arguing about the different DFT accuracy, which is like 5, 10 milli-electron volt. But here, I'm telling you that something that is 150 milli-electron volt away from the convex hull can still form. And in fact, it does, and it has very interesting mechanical properties, and there is an article in press about this, okay? Okay, all right, so now this is an example of the system. So this is the number 2, you see that is it's a single phase, polycrystalline single phase. And this is an example of polycrystalline multiphase one, right? And if you look at how the metals are dispersed, you see that this line corresponds to this line corresponds to this. Here the metals are all pretty much random, and you see there is segregation here for the multiphase. Here there is segregation of more metal or less metal, so metal rich or metal poor, depending on where we are looking. Okay, so single phase, multiphase. Okay, so now now I only told you an on-off. Do they form or don't they form? So now let's go beyond this and let's try to understand more from this vector of population that I mentioned before. And this is the idea of this article of Yoav, Cormac, Vecchio, and myself, which led to the method LTVC miscibility gap. And now other people are expanding this method, somebody in this audience like Simon, to find other feature in the phase diagrams. Okay, so now why we do first, why we are interested in the miscibility gaps. Okay, let's go back to the theory. This is the miscibility gap. We are interested in the miscibility gap because we were interested in the melting point. And why so? Let's start again from a simple thermodynamics. If I have an isomorphous system A and B, right? So and they will mix alpha and let's all solid solution and liquid, right? You're gonna have something like this, which is a length phase diagrams. But if A hates B at low temperature and B hates B at low temperature, there is a little bit of hate in between each other, but very little. Then if you decrease the temperature, you form this line here, which is, again, I told you before, it's called miscibility gap, all right? By the way, the gap is versus X, is not versus Y. And the top here is called the critical temperature. Okay, what does it mean? It means that at low temperature, they will have a mix of A rich and B rich, and at high temperature will have a random, okay? But this is also associated with the decrease in the melting. This has been known for 200 years. So the clustering tendency of the solid, which means that A prefers A more than B prefers B more, leads to higher segregation in the low temperature and brings melting depression. If you look at the phase diagrams, and I've been looking at phase diagrams for ages, you actually see that at these points tends to be below these points, right? So the melting depression goes down, right? And the minimum of the melting, which is called the congruent melting, it usually is nearby the same composition of the highest critical point of the miscibility gap, okay? You can play this trick more and more. You can increase the height between A and B and B and A. So a miscibility gap is going to go up until they touch, and this is the forms the eutectic phase diagrams, or eutectoid if this were liquid. Okay. So why we are interested in this? Because now let's go back to, let's do the opposite. Let's suppose that you have a phase diagrams, and the phase diagram has a miscibility gap. Okay, I'm running out of time, but please be give me another 5 minutes, okay? And suppose that now you are God, and you are able to put your finger here and bring down the miscibility gap. Wow, if you're bringing this down, then you will bring up the critical temperature of the melting. Okay, so there is a correlation actually between the miscibility gap critical temperature and the critical point of the congruent melting. Okay, so that's why we did these things, because instead of calculating this melting point, which is by far a disaster to calculate the melting for a 4 or 5 species systems, you're not going to be able to. It's going to take you forever. It's much easier, yet very difficult, to calculate the temperature of the miscibility gap. So this is a big problem. But this is a gigantic problem. So we calculate this as long, and we infer that as long as we have this distance. And we do have, because Yoav and Cormac went through the database and through CalFAD, et cetera, and actually calculated what is the relationship between this line, you see Tm minus Tc, which is this tanks, with respect to log of Tm, which in this case, well, it is this one, but it can be this one if you just remove it, right? And what we find from this all experiments, all right, we find that the more species you put, the higher gets the melting point, and the higher the entropy you have, the higher is the melting point. That actually was the message. So to get a very high melting point systems, you need to have a very low miscibility gap and many species. In fact, look at here, the highest known melting point system, which is tantalum hafnium carbide, right, Ta4 hafnium C5, which is the melting point, okay, is as a higher melting point than the two constituents. TAC is this temperature, hafnium carbide is this temperature, this is higher. You see, you get 60, 70 Kelvin more. And in fact, tantalum hafnium is a disordered solution because this is no order. So you have, this is rock salt where carbon is one position, and then tantalum hafnium, they are in 4 to 1 concentration mixed everywhere. All right. So this things is you can increase even further entropy if you put this mixture. Okay, instead of tantalum 4, you put molybdenum, et cetera, and if you, instead of having carbon, you put other species or vacancies. So that's the idea, to make a high entropy, high melting point systems. Okay, you can get better in this interpolation. This is really a MATLAB interpolation, a spline. Okay, there is very one-on-one machine learning. If you're interested in using CISO, like myself or Luca Ghiringhelli, you can get the CISO code. Now there is a CISO++ code that can be integrated in C++ framework, and you can put more feature, more than simple melting points, and you can get better parameterization of the features of the phase diagrams. Okay, there are some we have presented some of these updates in a review of Cormac and myself that has been published last year. Okay, so you can get more of this information, but the physics, pretty much the idea is this one. Okay, so now let's how to make the miscibility gaps, and with this I will approach the end of the presentations. Okay, so you have the ground potentials here. So you see that you have the population, the probability of population with times their energy. Okay, here you have remember that you change composition, so you need to remove the Gibbs part, so mu times the composition, and then you guess an entropy. The entropy is an x log x plus the loss of entropy that you get when you go from above to below the line, from disorder to order transitions. Okay, this p tilde is it's a big calculation of the degenerations, because there is a trick here. You have two look carefully. You have two concentrations. You have the small x and the big X. The big X is really the big macroscopic compositions. I give you 10 well, I give you 1 million blue atoms and 1 million yellow atoms. That's it. So you're 50-50. But then you shuffle them around and you create the small tiles. The small tiles have these compositions. One can be 60-40, the other can be 33-76, right? Okay, so those are the microscopic composition and those are the macroscopic. So there is a lot of ways you can distribute the microscopic composition to get the macroscopic ones. Okay, and all these things is calculated by IAIFR. So you see that you have the microscopic degenerations and then degeneration of the factor group. So you can get all these various p, and it tells you what is the weight of that particular configurations. Okay, and now let's do it. So how do we solve this problem? It's very simple. Lagrange multiplier. So you minimize everything and you get this text, which is the IAIFR population vector. This is exactly the population vector that I told you before, where this is the activation energy. But now there is this part. Okay, so this is the Gibbs part. So instead of being a Boltzmann population vector with a Boltzmann probability, this is a Gibbs population vector with a Gibbs probability. Okay, and therefore you can change the concentrations and go off stoichiometry and find and instead of going up and down the phase diagrams, you go left and right and find pretty much whatever you want, the solvus, etc., etc. Right? There is normalization, but forget about it. Okay. Now, what do we do with this population vector? That's the trick, because let me tell you, you have calculated 1,000 of them. Hundreds of thousands. You can put clusters, you can put machine learning, you can do as many as you want. You put, it's like a minestrone, you put them all. So you have an hypervector. And now what do you do in hypervector? Well, it's something that moves with respect to composition and with respect to temperature. Beta is temperature and mu is composition. So you can change how this object changes. Here we only change the temperature. If you go at 0 temperature, you are promoting only a very well-defined number of configuration, 2, 3, depending on the convex hull. So this vector has a very well-defined direction in the space. Okay, just an arrow, right? This arrow. If you are infinite temperature here, all the states are equiprobable. That's SQS, right? Okay, so where there is nothing, there is no thermodynamics anymore. So if every state is equiprobable, then the vector is not going to be in another directions. It's the same vector, but you are changing but it's a different directions. So you can calculate the angle with respect to the two. You fix a reference. I don't remember where I fixed a reference, but I think I fixed a reference to infinite temperature, which was easier. Okay, and then you calculate the angle, right, of your vector with respect to the reference. Okay, then you lower the temperature. Here you see you lower the temperature, or you change the chemical potential if you want to go in the grand canonical, and then the positions in which you have the highest change of this vector, because this vector really moves slowly. Look my hand, right? It moves slowly, pa, moves suddenly, right? Pa. In the position in which you have this big jump, and you can get it from the gradient of the angle with respect to temperature, is the miscibility gap. That's our definition of miscibility gap. If you do this, okay, and you put this definition inside back, you find that this change of entropy is exactly the Kullback-Leibler divergence, which is the population vector of the entropy above divided the population vector of the entropy below. This is very important because this Kullback-Leibler divergence does not measure entropy. It can go to 0. It measures the relative loss of entropy. You say, I lost 50%. I lost 20%. So you can really go to zero, because zero temperature, there is no entropy. But you can say that in the limit, you lose 50% of epsilon. So you do not violate the second law of thermodynamics, that there is no entropy at zero temperature. Anyway, so bottom line, if you define the miscibility gap like this, and you change your chemical potential and you find all the other lines, you guess what? You find the miscibility gap. Okay. Again, how does this work with experiments? It works. This is a miracle. Look at here. This is tantalum zirconium experiments, right? This is niobium zirconium experiments. This is copper gold experiments. The black one lines are experiments. The green ones, red ones are 8 atoms per cell or 12 atoms per cell. Yes, for every 12 atoms per cell, I need to calculate 50, 100. But let me tell you, 50, 100 order cells, they are much cheaper than a gigantic tantalum zirconium experiments, which might take years to get all the miscibility gap. And look how it works. It's pretty much the approximation. It's very good, and it works very well. So now with for our metals and for our carbides, we can go online and plug all these things. And Corey is making the interface, and Corey and Marco are making the interface that is going to be all online. It's not ready yet, but you will plug the system. Is going to get also thanks to Simon, is going to get the LTVC, is going to get this population, and you will get the miscibility gap for free. Okay, just out of the database. Okay, so there are other things that you can do with this POC that you can, if you are interested in electronic structures, really electronic properties, you can calculate the valence electron compositions. You can calculate electronic excited states. I'm not really entering in much details, but we can show you. And I have some articles under referee, so I cannot really discuss right now. But in the future, probably in the next 3-4 months, I will show you some examples in which this disorder expansion works also for electronic properties. Something that people did not believe that could be possible. And now we can really nail electronic properties as a function of disorder. This is for vibrations. This is something that was done by Marco. We are very happy because you can actually, vibration in disorder system is a big problem, because people do with folding Brillouin zone, etc., bring everything to gamma point. Okay, because disorder is really P1. But actually, we did with our POC systems. Look at here. For every of this small configuration, we get the harmonic vibrations, all right? The harmonic free energy, the harmonic density of states, the harmonic everything, right? And then we make the convolution here. We make the convolution, and we get the disorder free energy. Okay, so you get the disorder density of states of a vibration, etc. This was this was published by Nature Communication. It was also featured in their websites, and you can get really for some system, you can get the vibrational density of states in the harmonic approximation very quickly. Okay, and we also found the most important things actually when we need the vibrations, because some people say we need the vibrations. Some people say you don't need the vibrations. Now we know when we need and when you don't need. Practically, if you are studying thermodynamics, excuse me, and your precursors, remember the precursor, you need to study precursor. The precursor and all the sub components that creates the decomposition of the final product, if they all have the same atomic environment, local atomic environment, which is something that can be calculated with Hagen is writing the code to calculate the atomic environment automatically for all our database. So anyway, so if you start from the outcome, if the outcome minus all the decomposition to the precursors, if they all have the same local atomic environment, you do not need to calculate vibrations, because they will all cancel out, right? Same atomic environments, similar vibrations, they cancel each other, because you are dealing with formation and energies, formation vibrational energies. So since there is this word formation, they cancel. On the contrary, if you go from a cubic or hexagonals and the outcome is a cubic, then you need to study vibrations. Okay, so that's why for the molybdenum, etc., carbide of before, we need vibration. For the hafnium, blah, 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 carbide, we do not need vibration. And now we know when we need the vibration, when we do not need vibrations. So automatically we can decide if we want to do these calculations, which take forever, months, or we don't have to do this calculation and we can skip them because the phase diagram is not going to depend on the vibrations. And now the last slides, and now I finish, you can study also anharmonicity. It's even a little more complicated. Here you just need to calculate, remember here, this you have the vibrational, the harmonic free energy. Now you can put the anharmonic free energy. In this case, you just change as a function of volume. All right, you make an even more complicated convolution. You get this is an article is be submitted. You get the Z, the partition function, and you do all the derivatives, and you can get the thermal expansions. So you can get the thermal expansion of a disordered system with respect to the ordered ones. And look at here, for this is an example for copper gold. On the ordered system works. On the disordered system, it does work. There is some there are some discrepancies in where order is together with disorder, because of course you have the phases that are coexisting. So there is pretty much one has one lattice space in the other is the other lattice spaces. So you should really do a Vegas law average. So this point peak is expected. Okay. Anyway, let me summarize. Disorder system. We have embraced disorder system since several years ago because we believe that disorder is unavoidable. We want more things. So disorder is going to kick in. To understand synthesizability when this disorder kicks in, it's all about entropy, because entropy gives you the latent heat. And the latent heat is important for nucleation. And you will find also, if you, for instance, in advanced manufacturing, 3D printing, when you have adiabatic zapping or non-adiabatic zapping, that nucleation depends on how the latent heat can go around and can change the way the nucleation happens. Okay, so we are working on these things, and we are extending all our databases, and more database. We are extending our codes. You will see a lot of updates in the codes in the next years, all about the disorder systems. And we believe that if you even add at the end, you add machine learning after we discover the key factors, okay, you will find the new materials and new properties. Okay, so there is let me do some advertisement. There are all these collaborators. There are even here too many to list, to mention. And in March there is this bulletin by MRS with this short review by Cormac et others, and you can download it, and it's very short review, like 2-3 pages, very short. And you see what we can do with Entropy ceramics. I'm always looking for students and postdocs, and feel free to send me an email with potential candidates. Last but not least, we have a list of we have a series of seminars. I see some people in the audience are taking our seminars. Please go here, aflow.org/seminars. You can click the people. You can click. You see the next speakers is Gianmarco. It's Gianmarco. If you're in the audience, thank you for your pictures. And then you can subscribe. And this is the people that are coming in 2022. This is 23. We are already filling up 23. We meet every 2 weeks. We meet in Zoom. We are free. Okay, we try to help people in Europe, but we usually meet at 3 p.m. East, so it's going to be 9-10 p.m. over there. So bear with us, but this is the best we can do to help Californians and the Eastern United States. The field is material science, material physics. We like theory, computation, and experiments. We want to learn. So you're going to see that all these people are very active in research, because we want to share research for free in Zoom. So we have no problems talking to each other, and we are a very friendly group. We are always around 50 and 100. Everybody's invited. Please subscribe, come here, and you're all welcome. Okay, thank you very much, and sorry about if I was 15 minutes too long. My apologies, and I'm here for questions. I'm sorry for having talked too much. Thank you.
Thank you very much, Stefano. So we'll take questions. Yeah, questions.
Hello?
Yeah.
Hello?
Yeah, I would like to know this your ceramics, the carbide ceramics, this quaternary or quaternary carbide ceramics, and the work mainly highly disordered and highly high entropy systems. At the same time, you are showing the mixtures, some of the mixtures having the improved melting point. Could you explain that?
Is this here? Is the idea is this one that okay, so look at here. You agree with me that if I increase the miscibility gap, I decrease the melting point. Okay, that's given by books, right? But now if you do have a miscibility gap and you already have a solid solution, okay, and if you are able to reduce the miscibility gap, then you will increase the melting point. This is one of the many ways to increase the melting point. Otherwise, you can have a system that is very strongly enthalpically bound, like a very covalent system. But this is the other side. So when you want to minimize the Gibbs free energy, or you put a lot of work in minimizing H, or you put a lot of work in minimizing minus TS. In our case, we want to maximize minimizing minus TS, which means that we want to maximize S, the opposite side. Okay. At the end, what really counts is the sum. Okay. So if you already have a system already that has a solid solution, if you can find a way to lower the miscibility gap, you will increase the melting point. And by going into experiments, this is what we saw. Okay. Right, this is simple an interpolation of experiments. So that's why we started mixing things and to increase the melting point. Were we successful? Yes, but not as much as we thought. So meaning that, are we going to bring this to 5,000? No, not that I know. Are we going to bring this to 4,270? Yes. 80? Yes. But not as much as we hoped. So we increased the melting point, but the space on the sky is kind of very flat. Okay. However, you have a lot of other properties that you can improve. Mechanical properties, etc., etc. I cannot really disclose them right now because they're not published. But you can improve the melting point a little bit, and you can increase. You can improve other properties, both mechanical and both electronic, by increasing the number of species. So I hope I answered the questions in the most appropriate way.
Thank you very much.
You're welcome. And feel free to send me an email.
Okay. Yeah. Other questions? Yeah, there was a raise hand, Ahmed.
Yeah. Thank you very much. My question is similar to the previous question, but I want to ask about ionic liquid and metal liquids. Are they same this miscibility case?
I have not studied them. I expect that there will be. I know why you are interested in those. I'm not studying them. I expect that there will be things that will be similar. Yes, but I do not know. I do not, because ionicity brings a lot of gigantic headaches, because when you have a ionicity, you have an ordering of charges, and therefore all these things that I told you so far really does not have any charge attached. Okay. Okay. So
thank you very much.
So
yeah.
charge.
Continue.
So charge. No, hold on 1 second. So charge is another degrees of freedom. And you might have ordering of charge. Oh, sorry, you might have a chemical disorder, but a charge order.
Yes.
So that in this case, this is going to kill your entropy.
Oh,
you understand? Exactly.
Yes, because symmetry and asymmetry.
Yes, this is going to kill your disorder. So you can study these things if you know the charge. Okay, now I tell you some tricks. Okay, our code to calculate symmetry only uses configurations, right? So meaning the name of the atoms, atom A, atom B, atom C, and then you feed, and A flow sim tells you what it is. But now If you want to study the symmetry of the charge, you can create a fictitious atom, okay, and put them by hand in your ink-car, and then feed the A-flow sim, and it's going to give you the symmetry of your charge distribution. You understand? Exactly.
Yes, yes.
You can do
Yes.
you exactly, because you call one molybdenum and the other, sorry, one silicon, one copper, one whatever, because at the end they're just names, right? Okay.
Yes.
And then if you have things with the same ionicity or the same what is name, the same oxidation state, you can give them same numbers, same names. But this becomes more complicated. Excuse me, because usually ionicity is not an integer, right? You have and then it requires something called a Bader analysis, and Corey here. You see this name here? Okay, Corey here, Corey Ozis. Corey Ozis is writing a paper on Bader analysis with A-flow that we are finishing the paper. Therefore, if you call me or Corey in 6 months, we're going to have a better answer for it.
Okay, thank you very much.
You're welcome. You're welcome. So you need to be careful because remember that even magnetism, you can have a chemical disorder, but magnetism can kill you, and then that's it. You have no entropy anymore.
Oh,
it's very complicated. Yes.
Okay. Thank you very much.
You're welcome.
Thank you very much. Thank you.
Stefano, yes, in your presentation, you mentioned that now that you have the entropy due to the disorder, you can see where the vibrational entropy might be important. Did you already look at that? Can you give us some hints already?
I'm sorry, I didn't hear you. Who's speaking?
Gianmarco.
Hey, Gianmarco. Okay, tell me. Oh, thank you for your pictures. So tell me. Okay, so can you repeat, because I didn't hear you well?
So the question is, you mentioned that thanks to your approach, you are now able to see the moments, the places where the vibrational entropy is important. And so
yes.
I was asking you, did you already have a chance to look at when it is? And can you give us a few hints about that?
Of course. You just get this article, and there are some examples where it is and where it is not.
Yeah, but because you were fast on that, just let me 2 seconds take note of your.
Yeah, take a picture. You have a phone. Take a picture of these slides. Yeah. So this one as the system where it's important, the system where it's not important. However, this was done by hand. Now, if you really want, because suppose since you are the king of optimates, suppose you want to do this automatically, you need to wait that we finish the code here, LAAO, local atomic environments, which is generated by Hagen. Then we will pass the code to A-flow. It's going to be inside A-flow. So you will click a button. It's going to connect with the Corey code that is going to tell the composition, and it's going to connect to the Hagen code that is going to tell us the atomic environment, and is going to give you a score telling you should you do or you shouldn't do.
Okay, thank you very much.
That's it. Remember that if you have infinite computers because you have unlimited electricity, you always should do, because you always have changes. But are these changes something that is important, like 200 Celsius, 300 Celsius, or this is changes of 10 Celsius? Remember, because 10 Celsius nobody cares, but 200 Celsius is important, because if the miscibility gap, let me go back to the stakes.
Okay, thank you very much, Stefano.
No, because the miscibility gap is important. Okay, here, right, there are a lot of phenomena that happens below, and they happen with respect to the distance from this line. So, which such as aging. So, if your line is off of 300 Celsius, you might think that this alloy is stable, but this alloy is having fatigue, or this alloy is, you think that is fatiguing, in reality is stable. So you see that this line, which is really people think is curiosity, actually is the gigantic problem, because it tells you when you need to start wondering about the kinetics of aging, the kinetics of fracture, the kinetics of nucleation of microstructure, etc., etc., etc. So There are all these TTT curves, and therefore knowing exactly where is this line with vibration or without vibration is a gigantic problem in material science.
Thank you very much.
I'm sorry if I answered too much. Thank you.
Thank you. Yeah. Christian has a question.
Thank you, Professor, for this nice talk.
You're welcome.
Yeah, my question is, knowing that Curie temperature can be determined experimentally easily, and it's difficult to determine it theoretically, which approach you use to calculate the Curie temperature here?
I don't have the Curie temperature. I do not have any magnetic of degrees of freedom. We have not done yet. I am aware that Corey is in the audience. Corey is interested in looking into this type of disorder magnets. I have no answer for you because I personally have not done it, so I do not know.
Okay. Yeah. Thank you.
I am sorry. I'm sorry. I would like to answer all the questions, but if I don't know, I don't know.
Okay. Thank you.
Exactly.
I have a question. So your calculations are DFT calculations, like the 8-cell, 12-cell DFT calculations. So why don't you use a machine learning potential?
You can lose machine learning potential because we need to discover if a physics is correct, because machine learning potentially generates another layer of headaches, because when you have these tanks, okay, when you have these energies, you do not really know how good they are, because you can only know a posteriori. So in our opinion, before you need to use the DFT and you need to use natural intelligence to understand when the model does work. And when the model does work, then you can use artificial intelligence to bring it to make a calculation that you cannot do by hand, because there are only finite number of people, right? Like how many we are, like 20, 30. So we are 20 people, like we cannot do 1 million calculations. So machine learning, in my opinion, needs to be deployed after we have understood what's going on. And in fact, this thanks is this paper by the CISO by Giringhelli and Runhai is actually an example, a very intelligent example, how to accelerate the understanding of the features that are necessary for machine learning. Okay. So if we think that machine learning is like an impenetrable box that you feed stuff and you get good results, let me tell you, the results are not going to be good. Garbage in, garbage out. We need to understand what's going on.
Okay, yeah.
That's my opinion. This is my personal opinion. Then once we understood, more or less, and then Gianmarco, and then Luca, and then all our buddies here tell me, oh, you are off 10 milli-electron volt. No problem. We know what is the error. But then we can employ machine learning, and instead of studying 3 materials, or like 3 here, or like the vibrations, we have only how many, 3 or 5, whatever it is, we can study millions. But only because before we had used the natural intelligence to understand what was going on. This is my personal opinion.
Okay, yeah. Thank you very much.
You're welcome. Welcome very much.
Any other questions? Okay. I don't see any other questions. So Stefano, please, we need your slides, so you make them available to us.
Yes, absolutely. I'm going to send you the PDF. I'm going to send you the PDF of the slides. There is only one animation, so it's not going to be a big deal. That's it. I'm going to send you the PDF. No problem.
Okay. Thank you very much. So
you're welcome.
Let's start.
Welcome. Thank you. And again, sorry if I was 20 minutes too late, but we are here to learn. And I think I was the last one of the day, so I'm not taking away time for nothing else. So thank you for your patience, and we are here to learn. Please enjoy, come to our seminars. The next one is going to be Gianmarco. Gianmarco, see you in a week.
Yeah, thank you. Yeah.
Okay, thank you. Okay, ciao to everybody. Thank you.
Yeah, thanks to everybody. Yep. Okay.